So the next talk will be given by Andrei. Andrei is a visitor actually here in Gulf, Hercules and myself. He's currently finishing his PhD at King Juan Carlos University, and we'll talk about some of his recent work that he's been doing here. And
thank you for the introduction. In my case, this presentation will be not so general. I will focus on a specific problem of graph learning. And in this case, the problem is about learning graphs and simplicial complexity from data. As Elvin said, this is a recent work jointly with Elvin here and my supervisor from Spain, Antonio. So for starting, some motivation examples. Basically, as you already know, we have access to huge data sets which are generated in networks. Often there is not available. We don't have access to that structure of the network. So what we want to do is to learn that structure, maybe because there are this structure carries very important information about the nature of the data. How we do that? For that we are using graphs. As you already know, this is basically an introduction to get used with the notation that we will use after that. So basically, we can represent a network using a graph with nodes, edges, and weights associated to each edge between the nodes. In that case, we also define some graph signals, which are these blue bars representing the signal associated with each of the nodes in the graph. And also a representation for the graph. As a representation for the graph, we use the graph shift operator, which can be seen as a square matrix S, and some useful example, most known examples are the adjacency matrix or the Laplacian. So with this notation, we are ready to start to define formally what the graph learning problem or network topology inference problem is. So we have access to some collection of data in each of the nodes on our network. We don't know the connection between that. So what we are doing is to apply some topology inference, some algorithms, some methods under certain assumption priors on the data or on the topology to try to find the optimal connections between nodes. In this case, we can see them as pairwise connections. In this work that I will be explaining today, what we are trying to do is not only focusing on learning links between nodes, but also some kind of higher order interaction, which in complex networks they may be important or explain our data. Before that, I will talk about some related work. And all these approaches, I basically classify them in two blocks. This first list of approaches are related to use data, in this case, or data X, which is defined on the nodes, to infer the topology of the graph, basically pairwise interaction between nodes. They use different approaches and priors on the data and also on the graph, but I don't have time to explain all of them, but basically we will focus on GL and GSR, which I will use them on the experimental setting. The next kind of approaches, which I have here, are based on estimating higher order interactions, but what they do is to assume that we already know the graph, this pairwise node interaction between nodes. So they use that information in different ways to learn higher order interactions between nodes. I also highlight these three methods because I will compare in the experimental result with them. So now what we propose is, instead of learning the topology and then inferring the higher order interaction, what we will do is to jointly infer the topology and the higher order interaction present in the network. And we will focus, in this case, on the learning simplicial complexes. So to do that, we first of all propose a model for data. We model the data, and then we will model the graph and higher order interactions. For modeling the data, we are using the autoregressive graph Volterra model, which has this expression. And in this expression, I would like to highlight this term, which is saying that our signal, part of our signal can be expressed from linear combination of the signal at other nodes. And this term says that part of our signal can also be expressed as a nonlinear combination. In this case, we are using product of signals to express the tuple, the combination of the other tuples of nodes. To be more clear with this part, I have an example which may help a bit. So basically, imagine that we have the signal at node 2. So this signal at node 2, we can express that signal as a linear combination from the signal at nodes x1 and x4, and also as a nonlinear combination product of the signal at nodes x1 and x4, which is represented with this node pair link between node 2 and pair 1, 1, 4.
What is capital R? What is capital R? The dimension of Y?
Capital R is the number of samples, the number of samples we have associated with each node. So what this represents the K3 raw product. So in this is how we model the data, and now I will focus on how we model the graph and higher order interaction. This is captured by H1 and H2, which I will explain right here. So basically, recalling that this is our data modeling. I forget to say it, but this matrix V represents some exogenous variable, and I will explain later in the experiments because we will assume that this variable is known or unknown. But coming back to our graph modeling, we separate the graph modeling we have the part of pairwise interactions, which is captured in H1. There is an example of H1. You can see it on adjacency matrix. So basically, the black entries represent connections between nodes, and also these node to pair interactions, which higher order interactions, which we model with node pair interactions. In this case, these entries relates nodes with edges. So it represents links between 1 and node link 2, 4, which are represented the same we have for the second node and the fourth node in this figure. So what we do next is to use this kind of structure in H1 and H2 to model simplicial complexes. In this figure, you can see that we have a filled triangle and a non-filled triangle. So in this case, if we have a non-filled triangle in our formulation, it means that the links between nodes 1, 3, and 4 exist, and there is no interaction, there is no node pair interaction between these 3 nodes. But if there is a filled triangle, so in our model, what we will have is connection between nodes 1, 2, and 4, and also some interactions, node pair interactions between these three nodes that we have here. So saying that, what we proposed is this formulation. So in this case, we are jointly estimating the node pair interaction and also node pairwise interaction and node pair interaction. And this is basically fitting our proposed signal model. We impose sparsity on H1 and H2 to limit the number of edges and higher order interactions. And this constraint is basically imposing that structure that I mentioned before. So basically, a filled triangle can exist. Basically, this node pair interaction will be different from 0 if these 3 nodes I, J, and K, are connected. If they are connected, this is the indicator function, then we can have a filled triangle in our formulation. As you can see, this constraint, this formulation is not convex, so we propose a convex formulation to deal with that non-convexity. In this case, in this formulation, as the first three terms are the same as previously, and what we change is the constraint using this penalty term where we impose group sparsity. So basically, this matrix Q groups the edges between the three nodes that we consider, and also the node pair interaction between three nodes. We group these entries in Q matrix, and then we impose group sparsity, minimizing the number of controlling the number of field triangles we have in our graph learning. So this is our approach, and now I will go to numerical results. First of all, I will start with some synthetic data. We generated data using the proposed autoregressive graph Volterra model. And in this case, we compare our algorithm, which is shown in green, with other approaches that I mentioned before. And then we compare in terms of the normalized error for H1 as we increase the number of samples. This is R, the number of samples we have access to. So we also compare with two scenarios. The first one is considering that we have access to that kind of exogenous variable, and the other one is assuming that this exogenous variable is not known. So in that case, we can see that our model outperforms the alternatives. We also compare in terms of the error, in terms of the estimating triangles, which are captured in this matrix H2. And we can see the similar behavior as is shown in this figure for H1. Next, what we did is to compare our algorithm with the alternatives in a real case data. In this case, we are using a co-authorship dataset, and what we construct the H1 and H2 matrices, assuming that for H1 the two authors are connected if they collaborate in the same paper, and the higher order interactions, triangles are present if more than two authors are collaborating in the same paper. So using that information, what we do is to measure the F-score for H1. This figure is measuring the F-score estimation for H1, and then in this table we also provide the results in terms of F-score and error for H2. And what we see that our model is capturing better the structure of, is modeling better the structure that we have in this data of the co-authorship dataset. And to finish this, to basically summarize, what we propose is a new scheme that jointly learns the graph and the simplicial complexes from the data. And what we assume is for modeling the data, we use an autoregressive graph Volterra model, and for model the network, we have a difference between modeling the graph using H1 and modeling higher order interaction, in this case, simplicial complexes, by using this H2 matrix. Our challenge was to formulate the presence of triangles with this trilinear constraint, and we solve it by using group sparsity term instead of that constraint. And we basically show some results in terms of synthetic and real data set. If you have some questions, so now it's time.